Welcome to the deep dive. Today you're joining us as we try to unravel, well, a really bizarre cosmic puzzle. It's the story of Ansky. This is a black hole system recently spotted, and it's throwing out these incredibly energetic, repetitive X-ray bursts.
Yeah, we call them Quasi-Periodic Eruptions, or QPEs for short. And honestly, they're so new, so strange.
They're really making us rethink things.
Absolutely. It's like a whole new class of high-energy flares we're just starting to get a handle on.
So our mission today in this deep dive is to understand these eruptions, right? Looking at the latest observations, the theories.
Exactly. And Ansky, which is actually the 8th system like this we've found, is particularly interesting. It's given us a lot to work with.
It's like the most talkative one so far.
You could say that.
Right.
It's extremely energetic, pushing the limits of, well, what we thought was possible in these kinds of systems, how energy gets transferred near these supermassive black holes.
Okay, let's untack Ansky then. Where is it? What are we actually looking at? Our sources, the Astrophysical Journal and Nature Astronomy, they've got the details.
They do. So Ansky is in a galaxy way out there, about 300 million light years away.
Wow.
Over in the constellation Virgo.
300 million light years.
Wow.
And here's a cool detail. It first popped up on our radar back in 2019, but not as X-rays.
No. How then?
As just a flash of visible light. Looked pretty ordinary, actually. It got the designation ZTF-19 Ansky.
Huh. Just a normal flash.
Seemed like it at first, but that turned out to be the first hint. The little breadcrumb trail leading us to these much more dramatic X-ray eruptions later on.
So that visual blip basically flagged the location for us. That's quite the cosmic detective story already.
It really is.
And these QPEs from Ansky, they're not just typical QPEs, are they? I heard they're like record-breaking.
Oh, they absolutely are. Ansky is, hands down, the most energetic source of these QPEs we've discovered, period.
Okay, most powerful. What else? The timing is also pretty wild. It sets records there, too, for how regular they are and how long they last.
How regular are we talking?
The big X-ray flares pop off roughly every 4.5 days.
Every 4.5 days, like clockwork. Almost.
Almost, yeah. That quasi part is important. But it's surprisingly consistent. And each flare lasts for about 1.5 days.
Wait, a day and a half. So out of a 4.5-day cycle, it spends 1.5 days actively erupting.
Exactly. Almost a third of the time it's flaring. That combination, the energy, the frequency, the duration, it's unique.
Okay, that long duration feels like a big clue. So
yeah.
What's the leading idea? How do you explain something bursting like that so powerfully, so often, around a black hole?
Well, the picture we're building, and Ansky really seems to fit this, involves a sort of cosmic dance. You've got your supermassive black hole.
Hundreds of thousands, maybe billions of times our sun's mass.
Right. Huge. And it's surrounded by a disk of gas and dust, the accretion disk. The theory is that there's a smaller object orbiting within or near that disk.
A smaller object, like a star. Or maybe just a dense clump of gas.
Could be either. Or maybe even a smaller black hole, though probably less likely. Something with significant mass, anyway. And it keeps passing through the disk.
Ah, okay. So it's not just orbiting peacefully outside it, it's punching through.
That's the idea. Each time it plunges through the gas disk, it stirs things up dramatically. It drives out these huge expanding clouds of super hot gas.
And those hot gas clouds are what we see as the X-ray flares.
Precisely. Think of it like skipping a stone across a pond. But instead of ripples, you get these massive explosions of X-ray emitting plasma.
That makes sense. But why is quasi-periodic? If it's orbiting, why isn't it perfectly regular?
Well, that's where the extreme gravity comes in. First, the orbit probably isn't perfectly circular. It's likely elliptical and maybe even spiraling slowly inwards.
Towards the black hole.
Towards the black hole, yeah. But also, the intense gravity near a supermassive black hole actually warps space-time itself. General relativity stuff.
Right, the classic Einstein effect.
Exactly. And that warping means the orbit doesn't perfectly repeat each time. It precesses, shifts slightly, so the timing between the plunges isn't exactly the same every single time. Hence, quasi.
Okay, so it's kind of regular, but with a wobble built in by gravity itself. And it's spiraling inwards. Does that mean this whole show has an expiration date?
It almost certainly does. We expect these eruptions to keep going until one of two things happens. Either the gas disk runs out of material,
or the smaller object gets too close.
Right. Gets torn apart by the black hole's tidal forces, or maybe even falls in completely.
Any idea how long that might take?
Well, the estimates are, frankly, startlingly short on cosmic scales, possibly within the next few years.
Years, not millions of years.
No, maybe just a handful of years, which is why observing it now is so crucial. We might be watching a relatively fleeting event unfold.
Wow, okay. Now something else stood out from the sources, Ansy's disk. It was described as massive. How's that different from the other QPE systems?
Yes, this is a really key point. In most of the other 7 QPE sources, the thinking is that the disk is pretty small and close in, probably formed from a star that recently got shredded by the black hole, a tidal disruption event.
Okay, like stellar debris.
Exactly. But with Ansky, the evidence points towards a much, much larger disk, extending further out from the black hole.
And what does that imply?
It might mean the orbiting object causing the QPEs is further out too. And that could be why Ansky's period, the 4.5 days, is longer than some of the other QPE systems we've seen. They tend to have shorter periods, maybe because the action is happening closer in.
So a different kind of disk, maybe a different kind of interaction altogether. Fascinating. And getting the data for all this, NASA's NICER telescope seems to have been absolutely essential.
Oh, completely. NICER's perch on the International Space Station is perfect for this.
Why the space station?
Because it orbits the Earth so often, NICER can point at targets like Ansky repeatedly throughout the day. For Ansky, between May and July 2024, it was observing it something like 16 times every day.
16 times a day. You just can't do that easily from the ground, can you?
Not in X-rays, no. And that high frequency, that cadence, was absolutely vital. It allowed us to catch the X-ray fluctuations, the ups and downs that actually define these QPEs. We might have missed them otherwise.
So it wasn't just about finding the flares, but tracking them moment by moment.
Precisely. NICER's fast response and its ability to measure the X-ray brightness very accurately led the researchers map how the ejected stuff evolved during an eruption.
What did they find out about the ejected stuff?
They could figure out quite a bit. Like, each eruption blows out this bubble of superheated material. It's roughly spherical.
Okay.
It contains about the mass of Jupiter.
Jupiter's worth of mass.
Yeah. And it's expanding outwards at incredible speed, around 15% of the speed of light.
15%. That's mind-bogglingly fast. The energy involved must be immense.
Truly immense. And it's amazing that NICER could even get these details. I heard it even had a technical issue recently, a light leak.
Yeah, I read about that too. But it's still delivered.
It did. It really speaks to the resilience of the instrument and the team. It shows how valuable it still is for this kind of work, what we call time domain astronomy.
Right, time domain astronomy. Can you unpack that term a bit for us?
Sure. It's basically the study of how things in the universe change over time. Instead of just taking a single picture, a snapshot, you're watching the cosmic movie.
Looking for things that vary, flicker, explode, move.
Exactly. Things like supernovae, variable stars, and, well, these QPEs. Anything that doesn't just sit there unchanging. NICER observing Ansky 16 times a day is a perfect example of time domain astronomy in action.
Got it. So, looking ahead, what's next for Ansky research and for QPEs in general?
Well, first, just keep watching Ansky. Seeing how these outbursts change. Do they get weaker, stronger, more or less freaked? That will tell us a lot about how the system is evolving, maybe testing that spiraling idea.
Refining the models?
Exactly. And more broadly, studying QPEs is really important as we push into the era of multi-messenger astronomy.
Okay, multi-messenger, that's combining different signals, right? Light, particles, gravitational waves.
Precisely. These QPEs, we see them in X-rays, which is electromagnetic light. But the underlying event, this object orbiting and plunging through the disk near a supermassive black hole, could potentially generate other signals too, maybe neutrinos, maybe gravitational waves.
Ah, so Ansky could be a source of gravitational waves too.
It's a possibility, especially these things called extreme mass ratio in spirals, or EMRIs.
EMRIs, that's when a small thing spirals into a really big black hole.
Exactly what it sounds like. A stellar mass object, say, falling into a supermassive black hole like the one in Ansky. That's one of the key targets for future space-based gravitational wave detectors, like ESA's LICE mission, which NASA's partnering on.
And studying Ansky's QPEs helps with finding those EMRIs. How?
By studying the light, the X-rays from QPEs, we learn about the orbits, the masses involved, the dynamics of these systems before the final plunge. It helps us model what the gravitational wave signal from the eventual merger should look like.
So the QPEs are like an advance warning system, or at least a preview, for potential gravitational wave events.
In a way, yes. It helps us understand the kinds of systems LISA will be looking for. It connects the light we see now with the gravitational waves we hope to detect later.
So Ansky isn't just some weird outlier. It's potentially a Rosetta Stone for these extreme gravitational events.
That's a great way to put it. Our understanding is definitely still, in its early days. Ansky is pushing us hard, making us build better models. It's exciting. It just shows how many surprises black holes still have for us.
Absolutely. And just to mention our sources again for everyone, the detailed look at the variations in the expansion model comes from Johin Chakraborty and colleagues in the Astrophysical Journal, just published May 6th, 2025.
Right. That paper really digs into the physics of the ejected clouds using that homologous expansion idea.
Can you simplify that homologous expansion bit? What does that model basically say?
Sure. Essentially, it means the cloud expands uniformly. Imagine drawing lines out from the center. The bits of gas further out are moving faster in proportion to their distance, like dots on an inflating balloon.
Okay, so it expands in an orderly way, not just randomly.
Pretty much. And that orderly expansion leaves specific signatures in the light spectrum that NICER observed, allowing them to figure out things like the cloud size and speed.
Got it. And the other key paper was the discovery announcement in Nature Astronomy back in April, led by Lorena Hernandez-Garcia, using data from NICER and other telescopes.
Yes, that one laid the groundwork, identifying Ansky as a QPE source in the first place. Those are crucial pieces.
Okay, so wrapping this up for you. Ansky is this incredible record-setting system showing us these quasi-periodic eruptions, these X-ray flares. It's giving us this unprecedented peek into how matter behaves right near a supermassive black hole.
Likely caused by a smaller object repeatedly hitting a surprisingly large gas disk.
And it's challenging our theories, pushing our understanding, and even connecting to the hunt for gravitational waves.
Definitely. And it highlights just how vital instruments like NICER are, being able to watch the sky continuously and catch these fleeting energetic events. But yeah, like we said, it's early days. So much more to learn.
Which is the exciting part, isn't it? And it leaves you wondering, consider this. If these kinds of incredibly powerful bursts are happening out there, hundreds of millions of light years away, what does that tell us about how galaxies themselves evolve?
That's a big question. These events inject a lot of energy into their surroundings.
And how will combining light, maybe particles, and eventually gravitational waves from things like Ansky change our whole picture of black holes? What other completely unexpected phenomena are still out there, just waiting for the right telescope, the right detector to reveal them?
The universe is definitely not running out of mysteries.
Not by a long shot. Ansky's just the latest dazzling clue.
Yeah.
Thanks for taking this deep dive with us.